All right, welcome everybody to lecture 12 of the spring 2025 version of Intro to Space Navigation. So we're going to be continuing our discussion of estimation theory from the previous lecture. We're going to wrap it up today. And after today, we will have gone over everything that you need to survive and thrive on homework 2. And in fact, we're actually going to include some coverage on part of homework 2 towards the end of the lecture today, maybe after the break. With that out of the way, let's get into the notes. And estimation theory part 2. And we're going to start by talking about something called batch estimation. So you may remember in the previous lecture, lecture 11, we talked about 3 different ways of solving a linear estimation problem, like what we have here, y equals hx plus some additive noise nu. Right? Now, type of problem, we talked about how we can solve it in a least square sense, or if we're comfortable applying, solve it in a weighted least square sense, or if we have a decent idea matrix, then we can solve this according to maximum likelihood estimation. So 3 different ways of problem, which I likened to different evolutions of the same Pokemon. So you've got Charmander, Charmeleon, and Charizard. We've got 3 different levels of complexity when you go to solve this. One of the things that was implicit in each of these problems, and I think I might have even mentioned this, if we have multiple simultaneous measurements, we can stack them into a vector. So this problem setup, y equals hx plus nu, assumes that x is the state of the vehicle, or the state of your spacecraft in this case, at one instant in time. And it must be the case that you're taking all these measurements at the same time, because if you're, let's say, I don't know, measuring some radio signal from the Earth to determine something about your position, and then a minute later you take a different radio signal from a different ground station on the Earth, right? That's 2 different measurements, but in the one case you're measuring your state at some time t, and then in the other case you're measuring your state at t plus 1 minute. Those aren't the same x, so you can't just stack them like this, right? That's not how that works. So you might say, okay, in real life, aren't we only ever going to get measurements over time? Like, when are we ever going to get a whole stack of measurements at the same time? The answer is almost never. Right? We almost never have a problem that's this simple. Usually we get several measurements over time, and then we need to fold them all in together to do some sort of batch estimation. So batch estimation is one of the ways we can solve this problem, right? Is to say, okay, using some dynamics, we're going to find some way to estimate the time at some, or the state of the vehicle at some time, even though the measurements are at a different time. So maybe you can imagine that using some tricks and some underlying knowledge of the dynamics at play, we can basically add some complexity to our equation to allow us to take measurements at time t1 and then use those to estimate the state of the vehicle at time t2. And that's exactly where we're going. Right? Now, another solution technique, apart from batch estimation, is called sequential estimation. And we're not going to talk about that today. As a matter of fact, we have a whole unit on sequential estimation later. Sequential estimation is, okay, forget the idea of trying to estimate the state of the vehicle at one time. We should keep a running count. Like every second we estimate, we re-estimate, we update our guess. So at every second, we're either folding in new information from some new measurement, or we are propagating our dynamics according to a model of the system at play. And then we are at any given moment either propagating or updating, propagating or updating, propagating, updating. That's a sequential estimator. And a classic example of a sequential estimator is what's called a Kalman filter. And Kalman filters are ubiquitous on spacecraft. I've not heard of a navigation system on a spacecraft that does not have a Kalman filter running. Usually it's an extended Kalman filter or an unscented Kalman filter. There's fancy variations, but the basic idea is when you have measurements over time, you can either keep a running total, which is sequential estimation, or you can gather all your measurements for a long period of time and then estimate your state in a great big batch. So sequential and batch. So today we're going to talk about batch. So to put that into words here, measurements are rarely available at the same time. In practice, measurements are often available periodically. So we can handle that one of two ways. We process them as they come in. This is called sequential estimation. Think Kalman filter. And we have a whole Kalman filter unit coming up. Or we can process all at once. And that is batch estimation, which we will cover today. And in a way, we've kind of already talked about batch estimation, and I've alluded to this. Or is a form of batch estimation, because you figure you're getting measurements of the state. You're not even measuring the whole state. You're getting a partial state measurement. So maybe you have the position, but not the velocity, or maybe you even have line of sight measurements over time, and you're using the dynamics, in this case, the dynamics of two-body orbital motion, to say, okay, let's estimate the full state at one time, given a bunch of partial states over time, right? So orbit determination is batch estimation. We're going to learn about a more general type of batch estimation, which does not necessarily require two-body orbital mechanics to be going on under the hood, right? But you get the idea. So several different measurements, processing them all into a full state. We've kind of done that before. We're kind of good at that already. So suppose we have n measurements collected at n different times. Okay. So let's say we've got some y vector at t1, and this is going to be some h1 x vector at t1 plus new 1. And then this goes all the way to some noisy measurement at some time tn is equal to some hn x tn plus new n. Okay. So because we're about to do a lot of t's, we're going to abbreviate. So for brevity, we will say that yi is the measurement associated with time ti, and then similarly xi is the state associated with time ti. Right. We want to estimate the state at a particular time. We can map states at different times to a common time using the word of the day, the state transition matrix, STM. If you remember nothing else from the batch estimation lecture, we need to remember the state transition matrix. Okay, so some of you might have heard of this term before if you've looked at control of linear systems, taken like a linear systems or systems analysis techniques course. You might have seen basically if we have a linear system, we can map the state at some current time to some future time using a matrix, and that matrix is itself dependent on the dynamics underlying the system. Right? So if we have an ordinary differential equation, or ODE, of the form x dot of t is equal to f of t x of t. So there's just a matrix F mapping your current state to its own derivative. So you can use this to solve this ordinary differential equation. It will have a closed form solution. So it has a solution of the form x of t is equal to phi t comma t naught x of t naught. Okay. So this phi is our state transition matrix, and our notation here, and this is maybe a little bit backwards, this is from t naught to t. So we're reading right to left here. The reason we do that is because we want the notation to make sense. We're saying, okay, this maps t naught to t, so x of t naught times phi t naught to t gives us x of t. All right, it's a little bit like a matrix multiplication notation, right? Because this is ultimately a matrix multiplication problem. So even though normally in English we read left to right, in this case we're going to read right to left. Okay. In this equation, phi is the state transition matrix, which has the properties hopefully it makes sense that phi with no gap in time, which is to say initial time to initial time, ought to do nothing, right? So in this case, it would be the identity matrix. Right? Phi dot, so the derivative of the state transition matrix, mapping t naught to t, is f of t phi of t. So we're saying here, the state transition matrix from the initial time to the current time multiplied by f, which is the same f that governs the dynamics of the linear system, gives us the derivative. So f maps phi to phi dot the same way that f maps x to x dot. Okay. Also, it stands to reason that this matrix should be invertible. You should be able to go backwards in time, right? No particular reason that you need to map forwards in time. So let's say we're going from ti to tk, and we invert it. Well, that ought to take us from tk to ti, right? So tk to ti is ti to tk inverse. Makes sense. Finally, you should also be able to daisy chain these things, right? So you should be able to go, for example, from ti to tk by jumping around. So you should be able to go, okay, well, really it's tj to tk and then ti to tj. J to k. The same way when we're doing like a direction cosine matrix, you can chain multiple of those together. You can go from the A frame to the B frame to the C frame, so on and so forth. This hopefully all makes sense. So ideally, these are all intuitive, except maybe this one seems a little bit strange. but this should not be a shocking revelation. Okay. So why do we care about the state transition matrix? Well, remember our original problem. We're trying to solve a linear system of equations, a linear estimation problem, but one doesn't exist, right? We're taking measurements over time, and so we must estimate the state at different times. Well, not necessarily. Phi, then we can take measurements at some other time and use them to estimate the state at some initial time. So here comes the neat trick. Y1 is H1 phi T1 T0 X0 plus new one. And then all the way down to yn is hn phi T0 to Tn x0, right? We're still estimating x0. So what we can do is we can stack all this into a giant y vector, and then we're going to have some matrix that looks like this. H1 phi T0 to T1, and that's going to stack all the way to Hn phi T0 to Tn, and then x0 plus some massive vector nu. And now, after all that work, we're back to a linear system of equations. We now need to consider this larger H matrix, right? But ultimately, this is a solvable problem using the techniques of the previous lecture. This technique combines all available data. Whether before or after the state in question. We'll just say before or after the time in question. So as I have written it, we're mapping back to some initial time, but you could just as easily map all this to a future time or a time that's kind of in the middle of the measurements, right? So this is just an example. Now, here's, you might, great, we have a miracle cure, we can just solve with this method. Not necessarily. We have to assume that the dynamics at play can safely be linearized, right? Whenever you linearize, you're approximating your problem, and that will bite you in the butt if you're not careful, right? So we have to assume that the dynamics at play can safely be linearized at these timescales. Right. So any questions on batch estimation? Otherwise, we have a very short discussion, and then I want to get into an example. All right, good stuff. So the next thing I want to talk about is a quick aside, something called observability. So those of you that have studied controls, you might have heard of controllability. Like, can a system be controlled to any state you want? Or can it be controlled at all? Or is it completely out of control? This is similar for estimation theory, which is kind of the twin, the other side of the coin to control theory. In estimation theory, we worry about observability. Is it possible to reconstruct the state from these measurements? And the answer is not always. Similarly to how we think about degrees of freedom, like how many degrees of freedom are there in a measurement, how many are there in the state, therefore how many measurements do we need? We also need to think about, is it possible that we have an unobservable problem? We might have a lot of measurements. We might have more measurements than we know what to do with, but they might not be enough to reconstruct the whole puzzle, right? If you only have corner pieces of your jigsaw puzzle, you can have 10 million of them, and it won't be enough to solve your problem at hand, right? So observability is one of the most useful and fundamental concepts in estimation theory. All right, got ahead of myself. One of the most useful and fundamental concepts in estimation theory. A system is observable if you can uniquely determine the state from the available measurements. And so this depends on your measurement geometry, the problem formulation, the assumption, the choice of states. It's tricky. Right? So this depends on measurement geometry, problem formulation, assumptions, choice of states. We will focus on, again, linear systems in this class. So we will focus on observability analysis for linear systems. So here's a great example. Right? Imagine you've got a base station on the Earth. And from this base station, you get a range estimate to a spacecraft. So you know that there is a spacecraft at this distance away from the base station, right? So here's your range, rho 1. Then you observe at some later time that the spacecraft is at some new range, rho 2. And then further, at some later time, you observe that the spacecraft is at some range, rho 3. And let's say you keep doing this. Let's say you take 1,000 range measurements. Right? That will never be enough to tell you exactly where your spacecraft is, because you can think about it this way. Couldn't you have a spacecraft trajectory that goes like this? And so there's your spacecraft at the end of that maneuver. Or couldn't you have one that goes like this? Right? Or could you have one that goes straight through? Right? So it's a little bit more complicated than just drawing whatever squiggly line you want, because if you have different ranges over time, you do have some clue about your spacecraft trajectory, but ultimately there will be an infinite number of trajectories that could explain that measurement. So if you have an infinite number of solutions to a problem, you've got no solution to the problem. And so that's the observability conundrum. So let's put this in more mathematical terms. Right? Consider the case that you have range estimates of a spacecraft over time. And you're trying to batch estimate its final position. In this case, you are only ever looking at one component of its position. So because of that, you're not going to get the complete picture. It doesn't matter how many measurements you have. So let's go back to the math. Recall the maximum likelihood estimation solution, or MLE solution. X star is equal to, remember, it's H transpose R inverse H, all of that inverse, H transpose R inverse measurement matrix, or sorry, measurement vector. Okay, so you can just think about it for a second. For this equation to have a unique solution, then this bit, H transpose R inverse H, must be invertible. Now, we also know that R, which is the measurement covariance matrix, it's meant to be an M. There we go. Measurement covariance matrix is symmetric, positive, definite. So by definition, this will always be full rank and invertible, unless you did something wrong. So our suspicion is then cast on the H matrix, right? H must have rank n, where n is the number of states. Now, H is a m by n, so that's taller than it is wide matrix. So what we're really saying is H must have full So you can think of it this way. This is the big kind of bullet point. The test for observability is are the columns of H linearly independent? So generally, when you're thinking about observability, you can get pretty far by just kind of thinking about it. It's like, okay, if I only have the range to the spacecraft, it doesn't matter if I have 6 range measurements in 6 states. It's like you're not really measuring 6 different things. You're measuring the same thing 6 times. You're only going to get one component of your position and no information about your velocity. That will not be enough to fully constrain the problem. You will have an infinite number of solutions, and an infinite number of solutions really means, really means no solution. Right? You can't solve that problem. Now, this might sound a little bit similar. If we go all the way back, or similar, might sound a little bit familiar. If we go all the way back to our singularities and gimbal lock in lecture 4, we talked about how when you're using Euler angles, or really just in general, you can find yourself in this nasty situation where your attitude transformation matrix becomes singular, right? You've lost information. You have something that is not invertible anymore. It's rank deficient. And in this case, it's not so much that you can't determine your Euler angles, it's that an infinite number of Euler angles would still get you to that same point. So you can't uniquely determine your Euler angles, right? So this should sound familiar. If your matrix loses rank, which is the same thing as if physically your gimbal is aligned such that you've lost information along one axis, then you have an unobservable problem. So it should sound a little bit familiar. So we want to be asking ourselves these questions. Later in this class, we're going to set up a sequential estimation problem where you have range, range rate, and bearing, and you have those over time, which does not give you the full 6 states of your vehicle, but enough of those over time is enough to pin down the full 6 states of your vehicle. So in a batch or sequential estimation problem, that is enough, even though you're never directly measuring tangential velocity of the vehicle. You can get away with that. And you can convince yourself of that. Now, in this case, I believe it becomes pretty nonlinear pretty quickly, but I'd have to go back and check. Whenever you're doubting the observability of at least a linear system, then a very simple check is to make sure that your H is invertible, or I guess invertible, whether H has full column rank is a better way of thinking about it. Okay, so with observability covered, I want to spend the rest of the lecture on one great big example of batch estimation, which is going to look eerily similar when you set your eyes on homework 2. It's going to be very similar to the in-class example. So after we go through this example, which will take a while, then we'll also go through and do a quick primer on homework 2 and kind of how homework 2 is different than this in-class example. And that'll be it. That'll finish up our lecture for today. So I want to keep pushing. Let's get about halfway through the example, and then we'll take a break. Any questions before we move on? All right, feeling good. Time for a batch estimation example. All right. Suppose to measure gravitational acceleration. We'll do this dropping a ball and taking measurements using a Doppler radar. The ball at height h0 and is subject to a constant acceleration So we can already start to think about this problem. Imagine you have a ball. You're going to be dropping it onto a Doppler radar system. So here's the ball. It starts at some H0, and let's say you've got a Doppler radar sensor, which is going to be measuring some component. Basically, you think of this as like the radar gun that the police use to determine if someone's speeding, right? That type of thing. So you're going to get basically range rate. You're going to get one component of the ball's velocity. And so I'll let you think to yourself, what is observable in this case? Is the full state of the ball observable? Can we determine its height? Can we determine its speed? Can we determine its acceleration? What can we piece together with a whole bunch of radar measurements, and what can we not piece together? Right, that is the observability question. And I won't answer it right now. I'm going to leave that as something you can pause and ponder. Okay. So VT, this is right back to high school physics, right? Velocity is whatever the initial velocity is plus some linear scaling in acceleration. So T minus T0. Believe we assume it starts at rest, but I haven't looked at that. Haven't looked that far ahead yet. We also know that its height is basically going to be a quadratic equation, right? It's going to be an initial height and then some term that is linear in velocity. And then also, I believe this should be V naught. And then also there's going to be some acceleration term, a over 2 t minus t naught squared. So what are we measuring? Well, Doppler isn't really measuring range rate directly, right? Doppler sensors, like this one, measure frequency shift of reflected light. So our measurement Y, that letter Y should kind of make your ears perk up because we've talked about that. That's been kind of our measurement letter. Y is really just this. It's going to be the frequency received of some signal minus frequency transmitted. So it's going to send out a signal, it's going to receive something, and it's going to measure this delta F, which is approximately -2 transmitted frequency divided by the speed of light times velocity. So we will assume a transmission frequency. I'm going to put numbers to this. Transmission frequency of 35.5 gigahertz. And we will say that the speed of light is 3 times 10 to the 8 meters per second. I know it's not exactly that. It's close enough for this class. Right. And here comes the data table. We collect the following measurements. So we've got time in seconds, and we've got delta frequency, which is measured in hertz. Okay, 0.2, 0.5, 0.7, 1.0. So we let the ball drop for 1 second. We take 4 measurements in that time, and we get 584.3 hertz. We get 1275.4 hertz. We get 1750.4 hertz, and we get 2431.5 hertz. All right. So now, what may seem like a simple question, but is actually rather difficult. What are our states? You might say, okay, well, typically we say position, velocity, and attitude. So let's say we try to keep track of, I guess position would be height, because this is a one-dimensional problem. and we'll want to track velocity, right? That would be a mistake. And we'll show you later that height is unobservable in this problem. Right? For now, I'm going to take my word for it. The state is going to be velocity and acceleration. And for now, it's because I said so. Later, we'll show that it doesn't work if you try to do it a different way. So let's try to estimate. Let's try to get initial velocity and initial acceleration, which is just constant. That's going to be what we try to measure. So we're not necessarily assuming that this ball drops from rest. It could have been dropped with some initial velocity. Okay, so we could think of our state is going to be a 2x1. It's going to be velocity and acceleration. So our initial state is our initial velocity and our initial acceleration, which is just acceleration. So we're going to try to solve for x naught. And so what is our measurement model? Well, let's think about it for a second. Y is negative 2 ft over c times v, and y is not a function of acceleration. So if we wanted to set this up, we would say that y is equal to negative 2 ft over c, and then 0. So it's going to be a 1/2. And then this multiplies velocity and acceleration. Right? So all we did was we took this equation that we already have and we rewrote it in matrix terms. You'll notice that we're not measuring acceleration directly. So you might say, oh, we're toast. We're never going to be able to observe A because we're not measuring it directly. Now, that's not necessarily the case. We'll see that once we do the next step, we introduce the state transition matrix. We actually are able to observe acceleration, but we are not able to observe position. Now, maybe this makes some sense. If you just think about it for a minute, right? If you take a ball and you let it drop and you measure its velocity over time, you see how fast it's speeding up, that even though you never directly measure acceleration, you measure acceleration indirectly because you're taking measurements over time, right? If you set up this measurement on the moon, things would look different, right? Whereas if you set up this measurement, at some later time, it would look the same. So it's not going to be a function of time. If you set up this measurement at the top of Mount Everest, or if you set up this measurement at the bottom of the ocean in some pressure vessel where there's, still no water, as long as the thing is allowed to fall, by free fall, then height doesn't really make a difference, right? That could be absolute height from the center of the Earth. Okay, then I guess you're taking into account the gravitational acceleration would still be different if you go deeper into the Earth. But if your ball starts 1,000 feet away from your sensor, or if your ball starts 10 feet above your sensor, your measurements would actually look about the same, right? So we don't directly observe height. Now, for now, we're just saying that based on vibes. We don't have equations to prove that to ourselves, but hopefully it makes sense that you're not actually going to directly measure or even over time be able to piece together your height. Yes, Michael, I see you have your hand up.
Yep. I'm not quite sure if I understand why the y term is a scalar here and not like the vector that we had it in the previous lectures.
So in this case, this is one measurement, and later we're going to stack them. So this is saying, I guess maybe I should say, should really say yi, and this would be vi and ai.
Okay, that makes sense. Thank you.
Yeah, absolutely. Good question. Thank you. So next, I want to talk about the state transition matrix, but I think we're at a natural pausing point. So it's, let's see, 6:49 for you. Let's call it here for a minute and take a break until basically the top of the hour. So that would be 6 for me, 7 for you. And then we'll spend the time after the break talking about the state transition matrix, which is really the meat of this in-class example. All right, welcome back. So let's finish up our batch estimation example. And we kind of left on a cliffhanger on this break. So we said that here's a measurement, and we know from our previous discussion that we're going to need to map our measurements. In this case, we're trying to measure the initial, or we're trying to estimate the initial velocity and the initial acceleration. So in order to turn this into a proper batch estimation problem, we're going to need the state transition matrix to move forward. So we need state transition matrix. We will explore two methods of either one would do, but I like to give both of these just to be thorough. And because depending on whatever future problems you might be solving, one of these methods might be more simple or the other one might be more simple. So this is the state transition matrix method 1. So this is an example within an example. Okay. We want the state transition matrix for this particular problem, and we know the dynamics that are underlying it. We know that phi dot is f phi. We know that phi naught, which is to say phi from T naught to T naught, is the identity matrix. And we also know that our state derivative is this, the relationship between the state and its derivative is the same as the relationship between phi and its derivative, and it's this matrix F, which we might like to better understand that matrix F. So let's say we've got our velocity dot and our acceleration dot. That kind of gives us this. So this method, method 1, works if you know F directly. You don't have to estimate it or put it together. Right? So what is the relationship? Here's V, here's A. V dot is acceleration, right? So V dot is 0 times velocity and 1 times acceleration. Now, acceleration we're treating as constant. We're saying this is a uniform gravity field, so A dot is 0. It's 0 velocity, 0 acceleration. So this is our matrix F. And mercifully, it's very simple. We can divide in this problem, because we know that phi is going to be a 2 by 2 matrix, right? We can divide phi into 4 scalars, like so. The matrix phi is going to be phi 1, 1, phi 1, 2, phi 2, 1, and phi 2, 2. So we can actually take this phi dot equals f phi and split it up into 4 scalar equations. Right? So we have phi dot is f phi, which is 0, 1, 0, 0 times, if I write it again, phi 1, 1, phi 1, 2, phi 2, 1, phi 2, 2. Now, if we multiply this out, what we get is phi 2, 1, phi 2, 2, 0, and 0. That's just matrix multiplication. So this gives us 4 scalar differential equations with 4 initial conditions. So we can go through and solve this element by element. Starting phi 1, 1 initially, right? Well, we know that the initial phi is the identity matrix, which means that phi 1, 1 initial is 1. But we also know that phi 1, 1 dot is phi 2, 1. Okay. Is that enough to solve the problem? Maybe not. I don't really know what this means. Let's come back to this one. Phi. So this is the top right element. Initially, it's 0, right? Because we start with the identity matrix. Phi 1, 2 dot is phi 2, 2. Does that help us? Still not really. Okay, let's keep moving. This is going to make more sense in a minute, I promise. Phi 2, 1 initial. So remember, phi 2, 1, lower left element. It starts off as 0 because we have the identity matrix. Phi 2, 1 dot is 0. Okay, we're on to something now. If phi 2, 1 initial is 0 and phi 2, 1 dot is 0, then we can confidently say that phi 2, 1 is 0 forever. Okay, now we're on to something. Okay, now let's go back for a minute, right? Remember the two that we skipped because we were confused? If phi 2, 1 is 0, then we can really say, okay, phi 1, 1 dot is 0 as well. Therefore, phi 1, 1 is 1 forever. Yeah, it's like a puzzle. It's like a Sudoku. It's all coming together. Let's look at the last one, right? Phi 2, 2. 2, 2 initial is 1, right? Bottom right element is going to be a 1. Phi 2, 2 dot is 0, which means that phi 2, 2 is 1 forever. Okay, let's go back to the other one that we skipped. Phi 1, 2 initial is 0. Phi 1, 2 dot is 1, which means phi 1, 2 is always changing. But this is the only one that is always changing. So phi 1, 2 is always changing. And so what's actually happening is, think about it this way. It starts off with 0, but it's got a derivative of 1, which means that after 1 second, it's going to be a value of 1. And then after 2 seconds, it's going to be a value 2, right? What's really going on here is that phi 1, 2 initial is t naught minus t naught, which is just 0. But more generally, phi 1, 2 is t minus t naught, or delta t. So really, this is time, right? The derivative is 1. It is changing with time. You're basically measuring seconds since the start of the experiment. So our total phi, so overall, we have reconstructed the full grand state transition matrix from initial time to current time. And that is going to be 1 time minus initial time, 0, 1. There it is. So there's our answer. We can go back and solve this problem. But this was kind of hard. At least in this particular problem, we kind of had to go through and solve 4 different differential equations with 4 initial conditions. It was a little annoying. There is another way to do it, a way that I think is easier, but I wanted to show you both methods so that you're empowered to do what you want to do on the homework assignment. Method 2. And we're going back to our good old friend, matrix vector calculus. Right? Phi from the initial time to the current time is really the derivative. It's almost a Jacobian, right? You're looking at the sensitivity of the current state to the initial state. So it's the derivative of the current state with respect to the initial state. Okay, so if our full state x of t is velocity as a function of time, acceleration as a function of time, which that's really just v naught plus a t minus t naught, and then acceleration of t is a constant. It's just a or a naught, same thing, right? I guess we'll say a naught. And then x of t0, which is the initial state, is just v naught, a naught. I use a naught and a interchangeably throughout this problem because a is not changing. So how would we go through and do the derivative? The derivative of our state with respect to our initial state is going to be derivative of velocity with respect to initial velocity, derivative of velocity with respect to initial acceleration, derivative of acceleration with respect to initial acceleration. Oh, got ahead of myself. Initial velocity, and derivative of acceleration with respect to initial. I've been two mistakes. There we go. Okay, and in this case, actually, maybe I got excited. It's not quite matrix vector calculus. This is just regular old calculus, right? So derivative of v with respect to v naught, well, that's 1, right? Derivative of velocity with respect to a naught, that's t minus t naught. Derivative of acceleration with respect to v naught doesn't exist, it's 0. And then derivative of acceleration with respect to initial acceleration, they're the same thing, so it's 1. There we go. So we just arrived at the state transition matrix that much faster. So this is my preferred method, but you might prefer the other one. It's up to you. Dealer's choice. Okay, so questions on how we arrived at the state transition matrix. Otherwise, we will get back to our solution and actually solve it. Good to go? Okay. Returning to our Doppler batch estimation example. Okay. What we really want to do is we want to say h at time k, and then phi mapping from t0 to tk is going to be, remember, h is -2 transmission frequency over the speed of light, and then 0. Then we multiply by 1. In this case, it's going to be tk minus t0, 0, and 1. And if you multiply this out, what we get is -2 transmission frequency over c, and then -2 transmission frequency over c tk minus t0. And this is what we stack. Right? So we're not just going to be stacking our h vector, or our kind of h 1/2s. We're going to be using the state transition matrix. We go through and we multiply it out. This is what we stack. All right. So in our case, t0 is 0. So for us, our case, what this is going to look like is some noisy measurement y1, some noisy measurement y2, some noisy measurement y3, and some noisy measurement y4 is equal to -2 transmission frequency over the speed of light. So we're going to factor this out of our matrix. And then this is going to look like 1 T1, 1 T2, 1 T3, 1 T4, which is a full column rank matrix. We're going to call all of this, and then this is going to be V naught A naught. So we already have everything we need. We have basically a y vector, we have an x vector, we have an H matrix. This is our linear estimation problem, or estimation theory problem. We can solve this using the least squares, H transpose H inverse H transpose Y gives us X. Or we could take it a little bit further, make this an MLE solution if we need, if we have the measurement covariance matrix R. So for an MLE solution, we need R. Okay, if we say the measurements are corrupted with some noise, and that noise looks like this, zero mean noise, but it has sigma delta F of 5 hertz. Then R is sigma delta F squared identity 4 by 4. So we're saying, okay, along the diagonal of the identity matrix, we're going to multiply by the sigma delta F squared. Okay. Now, what you're going to notice here is that we're not giving different weights to each of the measurements, right? As we've written this, we are as unsure about the first measurement as we are about the fourth measurement. So the incorporation of this R isn't really going to change our final answer all that much. In fact, I don't think it changes it at all. But what it will change is our covariance. So hopefully that makes some sense. If we say, oh, you know what, guys, I'm really not sure about my measurements. And you go, okay, that's fine. Which one are you the most sure of? And you're like, well, I still want to treat them all equally, but I'm not sure about any of them. Then if you continue to treat them all equally, you're going to get the same answer as your least square solution. But if you jack up your uncertainty, then what's going to happen is your covariance, your well, I'm really sure I'm in this blob, that blob's going to get bigger. Hopefully that makes sense. Now, if we had chosen to weight the measurements differently, then we would actually get a different answer. And we'll see this on homework 2. So then calculate our state. And it's going to look like X star is H transpose R inverse H transpose R inverse noisy measurement vector. And I'm just going to give you the answer. And I would highly recommend you go through and code this up as a warm-up to homework 2. So you can kind of convince yourself that this works. X star is negative 0.518, negative 9.773. And in this case, the true solution, the actual numbers that were used to generate this problem, is that our initial velocity is negative 0.5 and our acceleration is negative 9.81. So we are in fact doing this measurement on the surface of the Earth at sea level, not a shocker. So we're pretty close. We're pretty close. There's noise in our measurements, which means that we are not actually going to get the right answer. Let's see how close we were exactly. So pretty close. Our covariance is P is, remember, H transpose R inverse H inverse. And if we multiply that out, we're going to get 5.8 times 10 to the negative 4, negative 7.8 times 10 to the negative 4. This is going to be symmetric, negative 7.8 times 10 to the negative 4, and 1.3 times 10 to the negative 3. Now, I care more about the diagonal terms than the off-diagonal terms. First, this 1, 1 element is going to be the uncertainty in our initial velocity squared. So from this, can say that the uncertainty corresponding to our initial velocity is the square root of that first term. It is 0.024 meters per second. Make that clear. And similarly, our initial acceleration uncertainty is 0.036 meters per second squared. Okay, so let's think about it. Our velocity, we are off by 0.018, which is less than 1 standard deviation. Right? So we're saying, okay, well, look, I think I'm at negative 0.518, but here is my error bounds. I'm 0.518 plus or minus 0.024. And actually, yes, we are. Our acceleration, we're saying, well, look, I think I'm at negative 9.773, but really it's negative 9.773 plus or minus 0.036. Okay, so in this case, we are roughly 1 standard deviation away from the truth on both counts. Okay, and so on the homework, you'll be asked to do something similar. You'll say, okay, well, what is your answer? And I believe on the homework, I actually tell you the right answer to the problem. And I say, okay, well, how close were you, given the fact that we did ultimately get the wrong answer because we had noisy measurements? Okay. So we are roughly 1 sigma away from truth, which is pretty good. Now, note, and I said this at the beginning, trust me, we can't observe the height. Let me prove that to you now. What if we also wanted to estimate h naught? You can just think about it and convince yourself that this won't work. But if you insist, then our x vector becomes HA or HVA, so height, velocity, acceleration. And in this case, if you go through all the work, you find the state transition matrix, you do all that, then HK, so one column of your H matrix is going to be -2 transmission frequency over C, 0, 1, and T minus T initial. I can clean that up a little bit. The columns of H are linearly dependent. If you actually go through and try to solve this, you won't get anywhere. So what do we do about that? If your system is unobservable, you don't have a lot of options. You estimate fewer states, or you buy more sensors. Unobservable means that the information that you're giving me is not enough to uniquely determine the state. So either make the problem easier or get better measurements. Those are your options. All right. So with that, I want to pivot, talk a little bit about homework 2, problem 2, which I recognize I've not posted the homework yet. There's no way y'all would have started it, but just for your awareness, there is a homework problem which is coming up where you're going to be using some, I think homework 2, problem 2 is actually, okay, homework 2, problem 2 is not batch estimation. It's actually based on the techniques from lecture 11, but I set up the problem in kind of a weird way. So I'm going to stop here for a minute. Questions on anything we covered, because from this point forward, it's kind of bonus content. All right, cool. So with that, y'all are free to take off if you need to be somewhere else. Thank you for coming. But what follows is kind of extra content. And if you'll permit me, I'm going to up homework 2. Okay. And this is going to be post. But the first problem is you have a rover that is driving towards a beacon, and the beacon is putting out some sort of information that you can use to estimate, in this case, range, right? So you're getting a delta T measurement. And ultimately, following a procedure which is very similar to what we just went over in class, and we're measuring range and range rate. So rather than measuring velocity and acceleration, we're measuring position and velocity. But problem one is going to went over, but there will be some key differences you'll need to go through. Problem two is going to be kind of different. So problem two, we have a spacecraft that is in flight over a series of these beacons that are on the surface of the moon, and they're each putting out some radio measurement. In this case, actually, we're getting a Doppler measurement. So we're using that same Doppler measurement model that we just went over in class. And we're saying that this delta F is -2 transmission frequency over the speed of light, but this is a three-dimensional problem, not a one-dimensional problem. In the one-dimensional problem, what you have is your velocity scaled by -2 transmission frequency over c, and that gets you delta F. In 3D space, it is the projection of velocity onto the line of sight from the beacon to the spacecraft. So the beacon is not going to measure the spacecraft's velocity. It's going to measure the component of the velocity that is directly towards or directly away from the spacecraft. So I give you this measurement model, and then I say, okay, well, what you're actually, and I do this because the math kind of works out a little bit more mercifully when we do it this way. What you measure multiplied by the change in time. And so what we end up getting is some information about range. So if you send out a signal and then wait for it to come back, then that delta T gives you some information about the range from you to the spacecraft. But then also your change in frequency gives you some information about your range rate. And I'm saying that in this weird world, you're measuring those two things multiplied together. So delta F times delta T plus some epsilon, which is your measurement noise, and then a covariance matrix. So I want to go through, and I guess it's a little bit premature to talk about this because y'all haven't had time to thump your heads on the wall yet, but I want to talk about how I would go about setting up your measurement sensitivity matrix, your H matrix, to solve this problem. So I want to go back, and maybe we'll leave room for side-by-side. Is that going to work? Shrink this down. That'll do. So the next topic, maybe I'll do this in blue, is advice on homework 2, problem 2. Okay. So a common question I receive is, what is H in this problem? I get that the tilde because there's noise on it, sure. But then I get that my state is maybe the position or the velocity or something. What exactly are we trying to measure? Well, let's read the problem here. Construct a measurement model which allows you to set up a linear set of equations to estimate the velocity of the spacecraft in the beacon frame. Note that you may need to estimate additional states. Okay, so we're trying to recover the full 3D velocity of the spacecraft given 5 basically range rate measurements from these different beacons. And each of those measurements is not really a direct range rate measurement. It is this, it's scaled by transmission frequency and speed of light and all that. Okay, so what do we do? What is H? You build H. That is actually part A. Or I guess in this case, I didn't put letters to them. It's just the first bullet point. You build H. H is the measurement sensitivity matrix, which relates your state to your measurements, right? I, vector of our measurements, is related to our state, I, x. So I haven't told you what the states are. I said estimate the velocity of the spacecraft, you may need to estimate additional states. So let's start playing around with these equations and see if something kind of drops out naturally. Okay, so here is some base frame, and I'm just going to go through and copy my diagram, homework assignment. Here's some base frame, and then you've got your spacecraft. In this case, I kind of did like an Orion. There's Orion, and Orion is flying on by with some velocity v, and you've also got some beacon, which I just used a rectangular prism. And so the spacecraft is at some position r, the beacon is at some position pi, not meant to be like a play on words, rpi. This is r minus pi. And what I'm saying is that delta fi is -2 transmission frequency over the speed of light times the component of velocity along the line of sight direction. So that would be basically velocity transpose line of sight vector, which is just r minus pi over the norm of r minus pi, right? I just want the direction. I don't want the magnitude of that vector. Okay. Now, we also know, and I'm going to kind of cheat a little. In the first problem I'm giving you, delta t, in this case I, is 1 over the speed of light times rho I. And so we're saying, okay, the time it takes, so let's say the beacon sends out some signal or the spacecraft sends out some signal. We're using a very simple measurement, or this very simple model saying, okay, the time that it took for the signal to reach your spacecraft is essentially related to the range by 1 over the speed of light. So it's about as simple as you can get. But here's the thing. This denominator here, the r minus pi, this range, that's actually rho I. And remember, I told you that your measurement is not the delta frequency or the delta t. I said that your measurement is delta frequency times delta t. And so what you're going to get is -2 transmission frequency over c squared. This row cancels with this row, and you use r minus pi. Okay. So now what? Well, let's say that mic squared over -2 transmission frequency. So this mess, I'm going to call this yi. So the measurements I give you in the data table are mi, but if you scale them by c squared over -2 ft, that's yi. There's your measurement. And your measurement is just velocity transpose r minus pi. Or you could say it's velocity transpose r. So the velocity projected onto your position. In this case, it's not the direction of your position. It's just the dot product of velocity and position, which on its own is kind of a useless thing. But then it's minus, and I'm going to rewrite this as pi transpose velocity. And it's reasonable to assume that we know this pi. Okay. So then if we say yi with some noise is mi with some noise squared over -2 ft. Okay. That is 1 -pi transpose velocity transpose r velocity. So this first bit, velocity transpose r, is useless. It does not help us answer our question, but there's velocity. Right? So here, if you stack these together, you'll get your y vector, you'll get your h matrix, and you'll get your state. And my recommendation is that your state is your velocity and v transpose r. V transpose r is kind of just along for the ride. It's just a stowaway. We don't really care about it. We're after velocity. So with this, we are not done with the problem, but hopefully this is a great start. And just one more time, I recognize it's premature. I have not given you time to be stumped on this homework yet, but I wanted to put this here as a hint. You can refer back to this later whenever you like, or in all likelihood, people will get about halfway through the homework. Some folks will struggle, and then they'll come and they'll look at this and we'll help them. That's kind of the goal. But that's the way that I'd like to set up this homework problem. Okay, questions on homework 2? Otherwise, we're really done, not just done with the core content. Okay, sounds good. So I want to thank everybody for today. I'm going to post this recording, and then hopefully there should be no interruption in coverage for the people that want to watch this tomorrow. So yeah, thank you everybody, and I'll see you.